back. I've kind of lost my voice, so bear with me on this recording. I want to prove what might be called like a quotient rule for limits. So imagine you have a sequence of numbers, they converge to some number like 5, and then to find a new sequence, which is just 1 over the terms in your previous sequence, then maybe not surprisingly, they converge to 1 over 5. Right? Now, of course, all these numbers have to be non-zero since we're dividing by an. The limit has to be non-zero since we're dividing by that. And the way we're going to write this proof is by using what it means to converge. So for every epsilon, there's going to be some point in time such that after that point, the distance between our sequence and that limit is going to be smaller than epsilon. So it's a little interesting how this proof is going to fit together. So I'll put that known information up here and just kind of write down our sketch of maybe what we have. So, what do we do? Well, we take an epsilon arbitrary, we do our sequence minus the limit, and of course that's going to be 1 over an minus 1 over a. We simplify, get a common denominator, etc. And the point is that this numerator, a minus an, well, that we're in good shape, because an converges to a. We can make this numerator as small as we like. We can make it smaller than 0.001, or smaller than epsilon, or smaller than epsilon over a million. We could even make it smaller than, epsilon over a, the absolute value of a, or really anything like that. So we're the boss here. We get to decide that. And so the question is, how small should we make the numerator? And what might we be worried about? Well, the absolute value of a is some number. It's a positive number because a is non-zero, and we've taken the absolute value of it. At the same time, this absolute value of an, well, that's going to change, right? As n goes out in the sequence, an is changing. And what we might worry about, we might worry how tiny that denominator could be. Because if that denominator is super, super small, then when we divide by it, it's going to make our resulting number perhaps a lot bigger, right? If we divide by a small positive number like 0.00001, it has the effect of multiplying by 10,000 or something like that. So we're thinking how small it can be, and the natural thing to look at is to give that a name, right? The smallest it can be is basically the infimum of that absolute value. And so if we just let m be that infimum, then of course it's true by definition that m is a lower bound for that list of numbers, absolute value of an. And so if we do 1 over both sides, well, because these are positive numbers, when we do 1 over it, it's going to flip the inequality sign. And so now we have 1 over an is smaller than 1 over m. So let's see how this comes into our proof. So let's rewrite our proof. Okay, since an converges to a, we know there's some n, so that now I've sort of declared how small I want this property to be. I want an minus a to be smaller than m times the absolute value of a times epsilon. Let's just see if this works. So we kind of do the same thing we did before. We had all this before. And now let's see what I did. So here's an inequality. Where is this coming from? Well, the a minus an is still there. This absolute value of a is still there. All I've changed is I've replaced this an in the denominator with m. And that's, of course, coming from up here, right? So this inequality is coming from this part above the line. Now let's look at the next inequality. Let's see, what's changed? Well, here the 1 over a and m is the same. And now what we've changed is the absolute value of a minus an is the same as this thing, right? Is less than a times m times e. And that's, of course, coming up here, right? This is our bound that we use the Archimedean principle for. Actually, we really just used the definition of convergence. And now this equals sign, well, we're just doing arithmetic, right? We're just taking a times m and we're dividing by a times m and then we're done, right? So we've shown that we found a capital N so that for all points in the sequence after that, our difference between our sequence bn and 1 over a is going to be smaller than epsilon. So we finished that, and again, I always recommend after you watch one of these videos to take out a piece of paper and try to write the proof yourself. That's really the only way you'll learn really the sort of the details is to try to reproduce this on your own. And what you may notice is that I've slipped one thing under the rug. Up here, you may have heard me say that m was positive, and that's kind of what justified me doing 1 over m. Well, if we look at this, what is m? Well, it's the infimum of a bunch of positive numbers. It's totally possible that that number could be 0, right? And so we need to rule that out. And so in the book, they deal with this in an earlier section, in section 8, example 6. And I just want to kind of talk through the idea. I think that proof is actually written really clearly, so I really recommend reading that. But the idea is if you have a sequence, it's never 0, and it converges to a non-zero limit, then that number m, the infimum of the absolute values of the terms, has to be strictly greater than 0. And the sketch of this proof is, you think about it, well, most of the terms are going to be really close to the limit, right? And the limit's not 0. Right? So say the limit's like 5, then most of your terms are going to be really close to 5. And maybe a few of the earlier terms won't be close to 5. But then the infimum of all these absolute values, well, most of those things are really close to 5, and then you just have a few other things. And since none of those terms are 0, the smallest of them, has to be positive. Right, so let's just kind of see where we're going. So we're going to do the case in this number line here. I've drawn that, I actually just took a screenshot from the book. They've drawn it where s is positive. And, at some point, all of our terms after a point n are going to be within a distance of s over 2 of the limit, so that means they're somewhere in this interval here. And so now let's just kind of define this number m. I guess it's not exactly the same as the m on the previous slide, but we're going to take the smallest, of s over 2 plus all these earlier terms, right? Did I really even mean that? I think I don't even need to divide s1, all these numbers, by 2. I don't think I need that. But in any case, let's see if what I've written is true. So certainly m is positive, right, because it's the minimum of positive numbers, right? S over 2 is definitely positive because s is positive. All of our terms are non-zero. So when we take the absolute value and divide by 2, that's definitely a positive number. Okay, so we agree with this inequality and this inequality. So now, if I take the infimum of all Sn, well, let's see, if I look at a term Sn, well, after capital N, all of those terms are going to be in this interval here, right? They're going to be bigger than s over 2. So all of the terms from Sn and beyond are going to be bigger than s over 2, and all of the earlier terms, well, I don't know what they are, but they're certainly going to be bigger than the minimum of all of these terms over here. Right? So I realize there's one little typo on this slide. I think I should have just written Sn here with what's going on, but this is just a sketch of the proof. I really recommend reading that proof of example 6 in section 8, and I'm going to give my voice a rest here, but thank you for watching and sticking with me till the end. Have a great day. Bye.